But what we do get with the sampling process here is we get to change the let's do 64 n equals 64 trials of a binomial process, and we can very quickly get some estimation as to the counts that would occur, as opposed to waiting quite a while to build out the whole sample space for 64 trials of a binomial process. And we can run this multiple times. Again, oh, did I not change anything there? I changed that in the wrong spot. Let me just fix that. There we go. That should be more reasonable. We can experiment with this. We can look at this process almost immediately, and but we can see that it's not exhaustive, and we can see that very clearly here, right? We don't even cover 0 through 18 successes in 64 trials, and we don't cover 46 through 64. So what we might do there is increase the number of samples, and we can see it'll take a little bit longer, but it won't take that much longer. And now we are showing results in the range from 15 to 49. Okay, so you have that code, and with that, let's pull up this breakout. So I'm going to put this here, and I'm going to paste this code snippet into Slack. So you're going to run this code below and describe the difference in outcomes between the two resulting dictionaries, right? Where D1 is sampling 16 bits, or 16, n is 16 in terms of 16 Bernoulli trials in a binomial process, where num samples is 100, and one trial of 1,000 samples in D2, same number of bits, but more samples. So I'll go ahead and paste that in, and I will set a timer. Okay. All right, I'm going to set a timer for, let's do 4 minutes. And this is just a conceptual explanation after you run your code. Okay, so give me a thumbs up if you've gotten this code to run and you've looked at the results. Not seeing any thumbs up. Okay, so why don't we just walk through this and get a sense of what's happening here, and I'll talk us through it as we go. So let me grab that code snippet. And we're looking at two things here. We're looking at two sets of trials, and we have one trial of 100 samples, and then we have another trial of 1,000 samples. And if I run this, oh, built-in function or method object is not iterable. Where are we seeing that? Line 122. d1.values. Well, this turned out to be a troubleshooting exercise more than actually a challenge to interpret. Okay, looks like there was an error. So that should be with the error corrected. Let's find out if it is. Probably should have tested that before I pasted it in, but let's see. Okay, yeah. So I'm going to grab both of these outputs, and we can look at them side by side. This first one, has 100 samples taken, and the next one has 1,000 samples taken. And this is for 16 trials in that binomial process. Okay. So again, the one on the left has much fewer trials than the one on the right. 1/10 the number of trials. Well, it looks like, there is some difference between these two, right? Like we're seeing the probability of 4 successes in 16 trials is 0.04 for fewer trials, right? And for 4 successes as 0.022 probability in 16 trials when we have 1,000 samples. Now, there is going to be a discrepancy here, and you might imagine that the more trials we take, the fewer trials we take. Let's if we go to some extreme and take 30 trials, right? We're going to see a very sparsely populated dictionary, and some of these are going to be kind of just really erroneous. Our expectation here, it's 16 trials, and in a binomial process, we would expect the value 8 to have the highest probability, right? And that's not actually what we're seeing in either of these. But we can imagine that one of these is approaching, doing a better job of approaching our theoretical distribution. But neither of them is doing that amazingly well. And we can do better than this if we just take more trials of the sampling process itself. So I'm going to comment these out, and we're going to go ahead and do that. So I'm going to expand on this binary sampling dictionary and just run more trials of samples in order to gain more surety. Now, I want this to kind of lead you in a direction of thought, right? There's the one thought that, yeah, you take more samples and you gain a better understanding of the phenomenon. And that seems sort of just obvious, right? Now, how we tabulate these matters, right? So we take one round of n samples, num samples, right? And then we do multiple rounds of n samples and we average them together. Now, what does that look like in code? Why don't we do, let's do 500, not 5,000, but 500 trials of 1,000 samples. And I'll just call this function binary sampling. And I'm going to say CLT here in sort of vague reference to the central limit theorem, but we're not going to apply the central limit theorem explicitly here. We're just going to say, well, the more times we do this, the less uncertainty or the more surety that we gain. Let's see. Okay. So I'm keeping this num samples at 1,000, and I'm going to do 500 trials of 1,000 samples. So I'm going to make, again, just a collector dictionary, and I'm going to say, well, for whatever in range number of sample trials, right? And this is going to, this loop is going to call out to our binary sampling, what is it, DICT? Is that what it is? Yep. There we go. It's going to call out to that. We're going to pass in the number of bits and the number of samples, right, as are defined in the parameters. And then we're going to say for every key and value in d.items, we can say if that key is not in dout, then we'll put it into dout, right? Dout sub k is, except this time we're going to put a list, right? We're going to put an empty list, and we're going to say dout sub k dot append v, okay? So we're going to collect all of these counts into the related number of successes k for every round of these sampling, every round of this sampling process. And then at the end of this, I'm just going to clean this up a little bit, and I'm going to say for kv in dout.items, I'm going to average, I'm just going to say dout sub k, I'm going to average the counts, right? Which is just the sum of the value over the length of the value, right? This is our list of counts, we could say. I'm going to leave it as v, just to keep it short, and we can return the sub out. Okay, so that should work, and I'm just going to call this. And I'll leave those default parameters as they are. And let's look at the counts. So here are the counts. This will just be for k, v, in, again, we need to use sorted here, otherwise they'll be out of order. Sorted d.items. And let's print, as per usual, the key and the value. And then we'll look at the probabilities as well, okay? And we can traverse this in much the same way. This time, however, we're going to say v is going to be divided by the sum of d dot values. And why don't we, is that right? Yeah, why don't we round that? Yeah, let's round that to like 5 places or something. And so that will be our probabilities. Okay. And of course, that's going to take a little time to run, right? Remember, 1,000 trials took, well, that didn't take that long actually, but 1,000 samples took a while, and we just did 500 of 1,000 samples. And, interesting. What is going on there? Oh, well, I rounded it up to 1, and of course, every one of those turned into 0 if I do that. Okay, let's try that again. All right, so the first thing that we can look at here, though, might as well. Well, you know what? That's going to change a little bit. Here we go. We'll just look at it as it comes out now. I think this is kind of cool. We were lucky enough to get a 0 and a 16 at least one time in our averaged result. That could have been less than 1, right? Could have been 0.8. It could have been 1.3. It could have been something like that. And it's possible in 500 trials there were times where we had like 5 zeros or something like that. But notice how symmetrical this is getting. This is approaching just better symmetry. You know, we've got clearly the modal value 8, and then we've got 174.01 and 175.724, right? And these values are looking more and more symmetrical because we've done multiple trials of this sampling process. And then we can look at these probabilities. And rounded, they start looking, well, regardless of being rounded, but they look even a little bit better when they're rounded. If we were to sum all of these, you know, we'd expect to see 1, well, something close to 1, right? So if we want to approach the theoretical distribution, this is one way we can do it. We can call out to our sampling process many times, right? Maybe 500. Maybe we don't think of 500 as being enough. You know, maybe we do this 1,000 times. And, you know, as we saw, it wouldn't take that long to do so. Oh, okay, so let's start approaching something that I haven't really talked about too much. Let me make sure I'm not calling this function there. That's what I was looking for. Okay. So remember when we did the Bernoulli trial, when we showed a Bernoulli trial, right? Oh, I have it right here, actually. We can leverage this function in order to create a sampling approach that has a variable probability, which is kind of cool. So let's do that. I'm going to grab all this. I'm assuming I already have, actually I already have random imported, I believe. No, I do not. Okay, but now I do. Okay. So let's, what we've been doing so far is either choosing 0 or 1 without any real, you know, with a 50-50 chance. And we can leverage this Bernoulli function in order to change the probability of success on any given trial. So this is going to look very similar, actually. And, you know, to our prior process, this time what I'm going to do, well, I'm going to snag this generate n bits, might as well. And I should grab this next one too. How about binary sampling dictionary? Yeah, I'll grab both of those. And I'm just going to modify these a little bit to accommodate to accommodate being able to have a variable probability here. So instead of generating n bits, I'm going to say generate n successes. And you know, part of that is just to differentiate this from the prior function. Oh, sure. Yeah, I will paste in this code. And you probably want that as well. Okay. So instead of, I'm just changing this name so we don't have a name collision, but you know, I think it's also, when I think about a bit, I think of it in kind of a 50-50 way. Maybe that's just a, you know, a semantic thing, and it doesn't really matter in this sense. But we're going to think about Bernoulli as returning a success or a failure in our number of trials, in 8 trials. So with this, I can just say, well, I'll grab Bernoulli of probability of success, put that in here. So when we call this, let's say Bernoulli of probability of success, we need to also pass in the probability of success here. So let's do p success gets 0.5 by default. And with that, I think we should have a working function. So let's find out if we generate 8 bits. Okay, so that should give us a pretty even split. What if we put this at 0.1, right? It shouldn't be, at this point, it shouldn't be uncommon for us to get all zeros. And on the third try of this, we got 1, 1. So I think here we can see that this is likely working. And we can take this idea a little bit further, and we can observe a probability distribution that has a different probability of success. So why don't we do that? I'm going to call this, let's see, binary sampling, and I'm just going to change the name a little bit. I'm going to vary the probability, right? So I'm going to pass in the number of bits, and I'm going to pass in a probability. This time I'll just call it I'll just call it p, right? 0.5. When we write the binomial PMF, we'll probably just call it p, you know. And we build a dictionary. That's our collector. We do for whatever in range num samples. Binary gets, instead of generate n bits, we can pass in generate n successes. And we're going to pass in the number of bits, and we're going to pass in the probability. And then we can say, well, this number of successes gets the sum of the binary. I'll just call this k again. And I'll say if k not in d, d sub k gets 1, otherwise d sub k gets incremented by 1. So let me paste this code in, starting from up here, before we go too much further. And let's think about calling this with 1,000 samples. So let me snag one trial of 1,000. Is that what we want? That's what we want. Okay. And I'll just call this D. All right, so instead of sampling dict, we're going to call this sampling vary probability, number of bits, 16. Why don't we, I'll just change that to 8. Doesn't make a very big difference for what we're showing. And I'm going to change this to 0.3. I could change it to you know, 0.33 or 0.3333. At any rate, that's, you know, going to get us a dictionary that we can then traverse, right? So for key value in the sorted d.items, let's print the key and the value and see what we get. So let's look at this. Notice where the concentration is of successes, right? And that's, you know, that's where we would expect it to be. If we multiply 0.33333 by 8, we're going to be sitting right down there around 2. And, you know, sort of sitting across 2 and 3 a little bit. That's what we would expect to see. And that's kind of cool. Like we can take this same process and modify it just a little bit. We can just through rewriting, you know, kind of tuning the Bernoulli trial to accommodate different values of probability. And you know, again, we can arrive at some more concrete probabilities through that same approach that we committed up here, this binary sampling CLT. And just grab all of that. And I'll just rewrite this a little bit, right? So instead of calling it binary sampling CLT, I'll just add that we are varying the probability. And we've got the number of bits. Doesn't really matter, but I'm just going to set this to 8. And here we're going to put in a probability, 0.5 by default, num samples, num sample trials, and everything from there, we just need to call a different function, right? So dout, this is our external collector of each sample that we take, each sample of 1,000 Bernoulli trials or 1,000 binomial processes. And we say for whatever in range, number of sample trials, binary sampling dict, we're going to change this function name to binary sampling with the varying probability. We pass in the number of bits, we pass in the probability and the number of samples. We can say for key value in d.items, if k not, yep, all of this looks fine. Nothing's going to change there. And we return d.out. Of course, when we call this, we need to call it by its new name. And I'll use number of bits at 8, probability at whatever it was up here. Number of samples 1,000, sample trials 500, and we can look at this in the counts dictionary and the probability dictionary. We can look at the counts, we can look at the probabilities. Okay. So here are our counts. And here are our probabilities. And what we've done is we've again, we've gained confidence in the results in these probabilities that we're seeing. So if we ask the question, okay, well, you have an unfair coin. You get heads, 33.33% of the time, and tails the remainder of the time. What is the probability that you're going to get 2 heads in 8 coin flips? Well, it looks like it's around, 27%, roughly. And it's kind of interesting. We've got, I wonder if this is just a facet of this set of trials that we're seeing. Oh, you know what I may have done? Let me double check my code. Oh, no. So that should be correct. Let me run that again and see if we get different results. Oh, no, this does make sense, right? Because we're kind of straddling 2 and 3. These, with this 0.333, right? That should be right around 2.5. So we are seeing that reflected in the results. So what is the takeaway from this? More samples is better. More trials of more samples is better. But the real takeaway is, can you code something like this, right? If you have a sampling process and you take 1,000 samples and you want to approach the theoretical distribution, the theoretical distribution of the underlying phenomenon, how would you go about doing that? How would you go about starting to do that? Well, this is one way. You can just take many trials of that sampling process, and in this case, say 500 of 1,000, and you're going to start ending up with something that looks like the theoretical distribution. And we can qualify that later after, we could qualify it with a 0.5 probability, by comparing it to the counting results, the results of the counting approach. But we're going to head into understanding the binomial distribution through the probability mass function. So, with that said, let's look at the probability mass function for the binomial distribution. And I'm going to point out a couple things here. Combinations is in here, right? And I think you might realize why combinations is in there now, right? Because we're summing the bits, and we have all these different permutations that sum to the same count of bits, right? And so we can see the appropriateness of combinations when we're asking, well, how many successes are there in n trials, right? What's the probability of 5 successes in 7 trials? Well, there's going to be some component of 7 choose 5 in that, in the underlying math of that. And then we're looking at the probability, essentially the probability of the event occurring, and we also need to consider the probability of the event not occurring, okay? And this form, you're going to see throughout statistics, throughout machine learning. It's nice to be able to, let me say it like this. I will often advocate softly for people to memorize some things. And the reason I do that is that you will see the same constructs in one function that you see in another function. And that's my only real argument for it, is that you start seeing these emergent patterns. And it's nice if it's nice if you see a new function and you're like, oh, I've seen this before. Something that looks very much like it. Like if you do log odds feels like that. And, getting that feeling, I think, comes along with either a lot of use of these functions or through, some light memorization of them. But obviously, I'm not going to say, hey, you have to memorize anything. you can always look things up, and there's a whole world of things to memorize. What I tend to recommend is, pick a few things that you feel that are really curious to you, and, maybe memorize the functions from that, whatever those might be. And what you find in time, if you use a specific function enough, you're probably going to memorize it anyway. But I think this probability mass function in particular, you end up seeing, you see this construct all over the place. We'll see it in the geometric distribution as well. Okay, so let's think about other parameters of the binomial distribution, or what are often called moments, other ways of thinking about binomial. There are some really convenient aspects to binomial, and we're not going to get into this entirely, but sometimes we'll use binomial to make some kind of approximation on a normal distribution, for instance. But that's because we can do easy math here, right? And the normal distribution, some of the math isn't quite that easy. We'll do some fun stuff with getting probabilities out of a normal distribution when we get there. But I just want to point these out. We're not going to spend too much time on these. I'm just going to have you code them pretty shortly. The expectation of a binomial distribution is the number of trials multiplied by the probability, right? And we saw that with, 8 times, 0.33. I don't know what I did, something like that. And that is going to point us at what value we would see emerge the most in terms of the count of successes. The variance of x, the variance of a binomial distribution, is pretty nice. It's a pretty nice little convenient bundle right there, And again, we're seeing this, p times 1 minus p, kind of thing going on, and we're just taking that and multiplying it by the number of trials, which is really accessible, and I think that's a good reason why we focus so much on the binomial distribution and the phenomenon of binomial. Oh, you know what? I don't know if I pasted this stuff in. Let me do that really quick. Just this CLT with varying probability. No, I didn't. Okay. Just get that there. So a little bit, we kind of introduced notation as we go, and something that you're going to see, and when you come across it, I don't want it to, really throw you. The random variable x, let's say, the random variable x. X follows a binomial distribution, okay? This is how we might write this, that has n trials and probability p. And then, when you see that, we could describe a different distribution. We could say y, follows a Poisson with, lambda of something, right? So if we were to fill this in, let's say with where, x follows a binomial distribution, 12 trials with a probability of 0.7, we can start framing questions like, what is the probability that x is k, or in this case, I would maybe just give the actual value, like x is, I don't know, 4, right? And this is how we frame these questions. This is how we very often frame probability questions, right? The probability that x is going to be 4 is, well, we can solve this in a number of ways. Probably the way we would solve this one is by calling the binomial PMF. So I'm going to have you code the underlying components of the binomial PMF first. And I'll give you 4 minutes to do this. You're going to code factorial and combinations, both of which you've coded before. Okay, so yeah, you're just going to name the first function factorial, right? Factorial is going to take a number. Combinations, right, is going to have two parameters, n and k. You can use r if you want. It won't make any difference as far as the computation goes. Okay, so let me set 4 minutes and go ahead. All right, I'm going to go ahead and code this. I'll put this up. I'll just put this down here, I guess. Yeah. And this is pretty straightforward, right? We're going to just code the factorial function, which we've coded a number of times before. And that's just def factorial of some number. I'll just say n, and I'll set a product, and we'll say for number in range from 1 to n plus 1. Doesn't really matter if we do 1. I'm just going to do 2, and we'll say prod times gets num, and we'll return the product. And that should work. The combinations function, n choose k, is going to be, well, it's going to be the factorial of n, as we can see down there. And we can divide that by the factorial of n minus k, multiplied by the factorial of k. And do that. And I'm going to wrap all of this in an integer because it's a count, right? So it makes sense to have that be like that. So let me just paste that in. Actually, let me run this just to make sure I don't have an error in there. Let's do 5, choose 5. Okay, that makes sense. Let's try 5, choose 2. And that makes sense. Okay, great. Now, the next function you're going to write, if you didn't see this coming, is the actual binomial PMF. Okay, and this is, well, let's take 4 minutes on this. I think I have it in here as 3 minutes, but I think 4 minutes would be good. My recommendation is just, break this into parts when you code it, because, coding things like this, really, it's super easy, but it's also really easy to make typos. So, it's kind of hard to track them down sometimes. The longer these get, the harder that'll be. So let's do 4 minutes, and when we come back, we'll check to see if it's working. Let me know if you need a couple more minutes on this. If you do, give me a thumbs up, and I can add a couple minutes. All right, so I think this is pretty straightforward, right? We're just going to write this as binomial PMF n, p, and k, and this is just going to be combinations of n choose k, right? And when I am writing these, I'll like give myself a bunch of space and I'll just delete the spaces just so I don't get anything confused. And this one's, this one's short and sweet, so I don't really need to do this, but I just want to show you an option as far as that goes. And I can collapse all this down. And we can return all of that. Oops. All right. And now I'm just going to make up a question and see what the answer to that question is. How about on average, 3 out of 5, yeah, let's say 3 out of 5 cars that drive by, let's say, have an antenna. I don't know. Yeah, whatever. Let's just imagine that's a real question. On average, 3 out of 5 cars that drive by have an antenna. What is the probability that out of the next 20 cars, about 12 of them have antennae? And that's easy enough to solve. I can just say, well, let me define first n, k, and p. I think I did n, p, and k. N here, well, we've got 20 trials, right? We've got 20 cars that we are considering. And we've got a probability of 3 out of 5. So I'll just do that, 3 out of 5. And then we're looking for the probability that 12 of them have antennae. So this is the binomial PMF. And we can just put in n, p, and k. And we'll have an answer to that question. So it looks like that's right around 18%, which may strike you as being kind of high. It actually strikes me as being kind of high, but if we think about this distribution, right, I could say for, whatever, for k, actually, yeah, let's do k in range, and we'll go from 0 to n plus 1, then I can comment out that k, and we should be able to see, if I just print the value of k, and I'll do this, we should be able to see this distribution. And we can see that it goes from very small down here until we get to some peak right around 13. And, we can see the peak here, and then we get very small again. So our expectation is going to be right in here, right between 12 and 13. And how do we figure out our expectation? Well, that's pretty easy. We can just multiply 20 by 3 over 5. And that's going to tell us what we would expect to see here. So let me paste this in as a template. Okay. Sorry, one moment. And I'll include everything up to Factorial, just in case anybody doesn't have that. And then I'm going to have you answer a couple very similar kinds of questions. Actually, I'll have you answer those after we take a break. Let's take a 6-minute break, and I will see you all back here shortly. Okay, so the next breakout is just going to be applying that binomial PMF. I've got 3 problems here, and you're going to have 4 minutes to do them. I'll give it just a sec for people to get back. Imagine if we didn't have this PMF, we'd be referencing a dictionary. We'd be, we could still work towards solving these problems, right? We could have, this big averaging operation, averaging the trials of the samples in order to have some variable probability. But we just really don't have to do that, do we? We have a closed formula that's very convenient. And what you're going to generally find is that if you have a closed approach to doing something, you're probably going to do it that way. Maybe I'll just take a quick aside and say something about that. This is a concept that I usually bring up a couple times. In machine learning, often what you're doing is you're trying to predict something, right? It's kind of not like everyday programming where, programming in general is like, well, you write a program that does something, and it's this box, and, you put something into it, something comes out of it. In machine learning, a lot of the time what you do is there is some mysterious algorithm that already exists, and that's your box, right? And you feed this box a bunch of data, and what it does is it spits out another box, except that other box is, let's say, a predictor, right? And now you can give it new data, like some new data, and it gives you a prediction on that new data, right? So what you find, or part of what this entails is that program that gets spit out is one of tons and tons of possible programs, right? Let's say let's call this the function space f, and then let's imagine, I'm going to constrain this, but let's imagine that for the specific problem you're trying to solve, there's some subspace, let's call that, I'll just call it A. And within A, there are, so A is composed of viable functions to solve your business problem with some degree of success. Like any one of these will meet the threshold of success in predicting, let's say, a continuous value or a class, right? Like, you have pictures of cats, dogs, and pandas, and you're trying to predict, given a new photo, is this a cat or a dog or a panda? Any one of these should work, given this way of thinking about this. But what if you spend all this time and this processing power and this energy, and you find some function in here, and yeah, that works. That's great. And then you analyze it a little bit more, and it turns out that this function is, equally solvable by a polynomial function, right? Where, maybe f of x is, ax cubed plus bx squared, plus some kind of irreducible error or some kind of noise that I'm just going to call c. If you find a function that does this, you should use that function. As cool as your machine learning algorithm is, as complex, as amazing as it is, If there is a closed mathematical formula that will solve your problem, you should just use that. And you know that idea keeps coming back around and around and around. I have a friend who works in optimization of a dog food factory, like a major dog food factory, and collects all this information from all these sensors, and takes all this data and goes ahead and plugs it into like a really pretty amazing machine learning model. And after analyzing it, it just looks like a function, like a closed function. And it's literally like okay, well, you have f of x, y, and z, and that looks like, some relationship between these, some kind of rational and, polynomial relationship between those factors. And you don't need the machine learning algorithm after all. So that's a bit of an aside, but this is kind of my me saying that we've got these, we kind of invented these cool ways to approach understanding the binomial process, but at the end of the day, we've got the binomial PMF, and we've got the ability to leverage what we already know about binomial phenomena and just plug some values into a formula and get some answers. So with that, that's what I'm going to have you do. Let's take 4 minutes, and I'll have you answer these 3 questions, which you'll be able to answer using the binomial PMF. So let's just solve these really fast. I'll just paste this in and comment out the I'll just do this. Okay. The probability in 12 coin flips of a fair coin that you get 7 heads. Let's do that one. So n is, well, it's 12 coin flips, right? So 12. K is 7, because that's how many heads we're looking for the probability of getting. And the probability, we're assuming it's a fair coin, the probability is 0.5. So we can just print. I'm going to round this. You don't have to, but not the sum, but the binomial PMF. And what is it? NPK, is that what we did? NPK, yep. NP and K. And let's round that to 4 places. So it looks like that is about 0.1934. And I'm going to copy this whole thing and use this on the next problem. So sitting on a park bench, you observe geese. There's a probability of 0.3. Well, I'll just put that in there. That a goose walking by has black feet. What is the probability that 4 out of the next 12 geese walking by has black feet? So 12 stays the same, and that we're considering 4 of them. So that is going to be about, well, it's going to be 0.2311. So let's look at this last one. There's a, at the cat cafe, there's a 40% chance. Well, that already sounds like 0.4. That any one cat you see is a Siberian. What is the probability that 6 out of the next 14 cats is at the park are Siberian, or at the cat cafe, I suppose. Let's find out. It looks like there's a roughly 21% chance that the next 6 out of 14 cats will be Siberians. Okay, so I'll comment all those out. And we're going to think about the other common facet of these discrete distributions, and that is the binomial cumulative distribution function, the CDF. So we're always going to have something like a probability mass function or probability density function or something like that, and then we're going to have a cumulative distribution or cumulative density function. So when we're looking at this, let me just point this out. This might look a little intimidating, but notice all this is the summation from 0 up until k, and we've replaced k in every instance in here. So when I ask you to code this, there's a couple ways you could code it, right? You could code it in this form, right, where you pass in, you know, you have a single for loop that performs all these operations, or as we're seeing in this lower part here, you can simply get the probability mass for each one of these and sum them all together. So you could write out the whole thing, or you could do them, or you could call the PMF and just sum the results of the PMF over a range. So what kind of answers, what kind of questions can you answer with this? Let's look at this one. At the cat cafe, there's a 40% chance that any cat you see is a Siberian. What's the probability that 6 out of the 14 cats at the park or at the cafe are Siberians? You could ask the question, what is the probability that 6 or fewer? Or you could ask the probability of 6 or more of the 14 cats that you see at the cafe are Siberians. So those are answerable questions with a cumulative function. So I'm going to give you 4 minutes to code that out. You're going to code the Binomial Cdf. And notice I named this k high here. You could just call it k, but I think this is just informative, right? It's like saying, well, what is the highest value of k that we're going to consider? You're going to consider everything from 0 up until k, k high in this sense. So let me set a timer for 4 minutes and go ahead and code that. All right, so let's code this. Calling this binomial PMF. Sorry, binomial CDF. And this is just a simple accumulator, right? We're going to pass in n, I think before I did NPK, right? I should probably stick to that convention. NPK. Yep. All right, so N, P, and K high. Now, here's the thing though. If I'm going to set P to 0.5 by default, I am going to have to put it last. So that's something I should probably fix in the slides. But, you know, that's what I asked for, so let's do that. I'm going to make an accumulator, and I'm going to say for K in range, and we're going to check probability of everything from 0 up until K high, and we'll include K high. And then the accumulator is going to be incremented by the binomial PMF of N, K, actually N, P, and K. Right, that's how that's coded, NPK. I like NKP a little bit more. Okay, either way. We'll return the accumulator, and we can answer a new kind of question very easily. We can answer the question, let's say, well, let's answer this one. And that, how about, let's say 6 or more out of the 14 cats at the park are Siberians. I'm just going to change that to cafe because I keep saying park. Either way. Okay, so this isn't as straightforward as it might seem, but we want to consider the probability of 6, the probability of 7, the probability of 8, probability of 9, probability of 10, 11, 12, 13, 14. And what we can do here is, well, we can set K high to 5. And our probability is 0.4. Yep, that's right. And if I set that to, if I set K high to 5, I can just take the complement of it, of the result of this binomial CDF. So what this is going to give me, what binomial CDF is going to give me here, is the probability of getting 5 or fewer. But I can just take the complement of that, and then I'm going to get the probability of anywhere between 6 and 14. So I just want to give that as an example, and let's find out what that is. Looks like it's just over 50%, or just over a 0.5 probability. So we put that in the Slack. And I believe, yeah, we have a quick binomial CDF problem. So let's take 3 minutes on this. There are, oh, and I might need to explain a little bit of this one, I think. There are 8 components in parallel and functioning independent of each other. At least 3 of those components need to be operational for a given circuit to function. The probability of any given component being operational upon observation is 0.7. What is the probability that at least 3 components are operational upon observation? So you can kind of ignore this idea of in parallel. Just think of it as you've got 8 components in a circuit. They don't affect each other. At least 3 of them need to be working. There's a probability upon observation that, you know, of any given component, that component will be operating. So I'll set a timer for 3 minutes and go ahead and solve that. Okay, so let's look at this. I like these kinds of problems. This problem in particular, I think, is kind of cool because what it shows us is that we don't have to think about things happening after, one after another, right? There's just a kind of a state of this circuit, and upon observation, the state is going to, has these independent aspects, and if three of those aspects, if three of those components are working, then the circuit's working, right? And we can answer kind of a pragmatic question as a result. So 8 components, to me, that implies 8 trials, right? And the probability of any given circuit, any given component being operational is 0.7. And then what is the probability that at least 3 components are operational upon observation? Well, to me, this is going to be a k high of 2, and we're going to take the complement of that. So we can grab that, and 1 minus the Binomial Cdf of 8 trials. We're looking for this, that 2 or fewer are going to be operational. And when we're thinking about this, the probability of any given component being operational upon observation is 0.7. That looks like that should work. And it looks like we have maybe more of a reliable circuit than you might think, given that any single component would be operational. We could extend this to a more complex question. We could ask, well, what would our rate of what would our performance rate need to be for any given component to consistently achieve 99.5% operation upon observation, right? We can start answering other questions. We've got all the means to do that here. And we won't go through a problem like that because you don't need to know that at this point. But there are a lot of problems in Learn that look like that. So let's... Okay, so the next thing I'm going to have you do is kind of a convergence of a lot of things that we've already done over the last couple days. You're going to code the binomial PMF dictionary, and this should take 4 parameters. The number of trials, k low, which is the low value of k that you'll keep in the dictionary, k high, which is the high value of k in the dictionary, and the probability. Okay. So you should have, let me make sure you have everything you need. Yeah, you should have everything you need. Okay. I'm going to set 5 minutes for this and go ahead and code it. And when you get to a solution, go ahead and put it in the Slack. Oh, you know what? Let me pause this for a second. If you're already started on this, that's awesome. Let me answer this question before we get too far. Why is ki set to 2? The way that we can think about this, we've got 8 components, right? Got 1, 2, 3, 4, 5, 6, 7, 8. And we need at least 3 of them. So we need at least 3 of them to be operational. There's a 0.7 probability for any one of these, right, to be operational upon observation, which is a convenient way of saying we're not going to worry about that. So we're going to sum the probability of this one being operational, this one, right? Sorry, this one, this one and this one. Right, we're going to just sum any one of these. We could even call these trials, right? 1, 2, 3, 4, 5, 6, 7, 8. Now, the thing about a CDF is only going to give us from 0 up until some value of k, which I'm calling k high. That's what the CDF gives us. It gives us the probability between 0 and k high. And because of that, we want to figure out what is excluded in the question we're asking. If we're talking about 3 or greater, then that excludes 2 or fewer. So in that case, we can get the probability of 2 or fewer and get the complement of that, which will give us the probability of what we really want, which is all this. Does that help clarify that? Cool. Awesome. Okay, so I will set this to 4 minutes, and yeah, go for it. Okay, let's code this. So we're coding binomial PMF dictionary, and it's going to be pretty easy after everything else that we've done. I think this is kind of a nice denouement, really. So let's plug these in, all these parameters, and finish the function header. Okay, so n trials, we're looking at k low to k high, and by default a probability of 0.5. So we can just make a collector dictionary and say for k in range from k low, which will be included, to k high, which will make included. We can say d sub k gets the binomial PMF of n, k, and p, except it's n, p, and k, and we return that dictionary. And so if I call this, we can call this binomial PMF dictionary. Let's give this 8 trials, k low of 0 and a k high of 8. And I can say for k, v, and d dot items, print k, and I'll round v to 4 places. How about, well, let's do 6. Okay, so there's our distribution. And you might be wondering if you remember way back when, you might be wondering how this compares to our sampling process. So let me go find that. I think it was here. Did I plug in, what did I plug into that? Was that 0.5 that I put in there? Probability of 0.5, yes. Okay. And let's try do this, where we've got, we don't need to use this one with the varying probability, but it's not going to hurt anything. We'll pass in a probability of 0.5, number of samples 1,000, number of sample trials 500, and we don't really need to see the counts. We just want to see the probabilities, and let's see how well this actually does. So on the left here, we've got, try that again. We've got the results of our sampling process. And on the right, we have the actual theoretical probabilities. That's doing really well, right? Like that's very close. And I just wanted to bring this back because I said I would. Notice that this is actually doing very well. And if we were to, let's say, try to, do a ton of trials, we might not do as well on the edges of the distribution in terms of estimating the actual theoretical distribution. But for what I'm seeing here, this is pretty good. And I just want to, I think it's always good to verify the claims that you make. And I think that does a pretty good job of verifying that our sampling approach, like an approach that takes trials of samples, does lead us in a good way to a theoretical distribution. And of course, we can use this for we can use this sort of approach for more than just, oh shoot, I didn't, let's see if I can, yeah. I just need to comment these out, otherwise if I run more code, we're going to be waiting for that. We can build other phenomena, right? We could build some sort of interdependent sampling distribution, right? Where in what's known as dependent sampling, where if the first trial is failure or success at a 50-50 rate, if we get success, maybe that increases the chance of success. Or if we get a failure, maybe that increases the chance of failure. And so we make some whole new probabilistic process. And, you know, we still have sum of successes, very much like a binomial distribution, but we've invented a new distribution that maybe has some tuning parameter of, well, how much does the success of the first trial affect the success of the second trial? We actually have everything in this file to be able to build some other distribution, this thing that I'm talking about that has dependency between the samples. We could start estimating a theoretical distribution in regards to our sampling approach. And I think this is good verification of that possibility, of our ability to do that. And even if we don't have a closed mathematical approach, you know, we don't have a PMF, we might be able to start discerning a PMF. And I think this is one of the amazing things about the space of statistics, the space of data science. There, you can invent new things pretty easily. And, you know, I'm just going to encourage you to do that and explore ideas when they come to mind. So I'm going to code something really quick that is just a small adaptation of this binomial Cdf PMF, and I'm just going to make a binomial Cdf dictionary. Everything stays the same, except of course I call out to binomial Cdf, right? That's really no different. And then when I call this, let's say binomial Cdf, and we should see the results of, binomial Cdf dictionary is not defined. Oh. There we go. Float object cannot be interpreted as an integer. On line 282. Line 326, that is. Let's look at that again. Binomial Cdf dictionary. Why is that? I think when I pass this in, this has to be n. Let me just track that down. I think this is on the function call for this. N, K high, and P. And I think here, yep, that's exactly what's going on. N, K, and P. Pretty sure that's what's wrong. Yeah, there we go. So I think it's nice to view the CDF in this form. Notice that the probability of getting 8 or less successes in 8 trials, that's guaranteed, right? You're going to get somewhere between 0 and 8. And I think that's just a nice thing to see. And we can, if we change the probability of success on any given trial, that will allow us to see a different slope of this. And I think that's also fairly interesting. So let's say this is probability of success of 0.1, and let's see what that slope looks like. And because of how I'm rounding here, it's saying that success is guaranteed within 7 trials. If I were to take the round off of this, that probably wouldn't have been rounded to 1. But yeah, just notice how we start accumulating here. So, yeah, 3 minutes to spare. Usually we start in on Poisson a little bit, but I'm kind of glad we're not going into Poisson today. I really like the Poisson distribution, and I'm going to try to give a good basis for understanding it. I think it's, I don't know, it comes up in so many ways, and it has like these really cool components in it. The way that Euler's number exists within it is really interesting. Why Euler's number is there is that in and of itself is a fascinating topic. But the fact that, you know, there are tons of phenomena out there that we can talk about through the lens of Poisson is really cool. If you get a chance and you have the interest, I have a video somewhere floating around. Let's see if I can track it down. Oh gosh. On kind of finding Euler's number, right? Using Python. And it's you know, it's a tutorial of sorts, and it uses base Python. I don't think I do anything outside of base Python. Let me see if I can find it. Oh, yeah, there it is. So, and it's only like 25 minutes long. And all the code's exposed. There's a link to a GitHub repo for it. If you want to have kind of a deeper understanding of the Poisson distribution when we get to it, I think this is a nice thing to go through. And I try to structure this video in such a way that it takes the analytic approach that we teach in this class, right? So, you know, if you're working with dictionaries, you're working with lists, if you're taking some phenomenon and trying to explore it in some way, this video will lend itself very well to that, and also toward the technical interview. I think it's a good study video for the technical interview in that way. But yeah, that's it for today. Stay on if you have any questions. Otherwise, have a great evening, and I will see you on... Wow, my brain is malfunctioning because I stopped drinking coffee, and I can't remember if today is Wednesday. It is Thursday. Okay, I'll see y'all on Saturday. You know, if you have questions in the meantime, I'm kind of on a project, and it's a little bit hard for me to make